Feedback is a technique, a versatile technique, widely used in almost all branches of engineering. One can find this technique implemented for improving the system performance in electrical engineering, mechanical engineering, chemical engineering, in almost all branches of engineering. The specialty or significance of this technique, engineering technique, is that it makes the presence or interference of human beings unnecessary, redundant. It leads to system operation from manual to automation. It also gives better system performance. In electronics engineering, also it finds applications in the design of amplifiers. It is used. This technique basically involves bringing output signal, a part of the output of system, to input side, and after manipulation this signal is connected to the input of the system. Now the input to the system has two components: one feedback signal, another output of the input signal source. Sometimes these two together reduces the input to the system. In such case, the feedback is called negative feedback. Sometimes these two together increases the input to the system. In such case, it is called positive feedback. Positive feedback is associated with unwanted oscillations, causing instability. For this reason, it finds very few applications. It is hardly used. It is the negative feedback that is widely used, implemented in engineering. In the design of amplifiers, it is used mainly to stabilize the gain, to adjust the values of impedances, input impedance and output impedance of the amplifier, and also it is used to reduce distortion, to reduce noise, to improve the bandwidth. Analog circuits, feedback amplifiers, part 1, series on semiconductor devices and circuits, lecture number 9.10. Amplifiers are electronic circuits used to provide strength to a signal, used to enhance the amplitude of the signal. These circuits, amplifier circuits, usually they are associated with certain drawbacks, like their performance. It is not stable, it is not fixed. It varies from circuit to circuit in which the amplifier is introduced. It varies with time, with aging. It also varies with the temperature. This variation is considered to be a serious drawback, a serious shortcoming. To overcome, to eliminate this particular disadvantage associated with the amplifiers, a technique is implemented. Feedback technique is implemented in the design of amplifier circuits. Once implemented, the amplifier becomes feedback amplifier. Feedback actually is a technique, a circuit technique, in which the output of the amplifier, it is sampled and then manipulated and brought to the input side of the amplifier and connected to the input terminals of the amplifier by proper sampling, by proper mixing at the input terminals, and by proper design of manipulating circuit that manipulates sampled output, it is possible to overcome most of the disadvantages, shortcomings that are mentioned, that are associated with bare amplifier circuits. In the present session, the focus is on basic definition of a feedback and also the need of a feedback for improving the performance of the amplifiers. Now let us move further to begin the course session. We begin the session with a few words regarding a feedback concept. The concept of feedback involves feeding a small fraction of the output at input by providing a connection from output to input. Feeding, giving input, connecting to the input terminals. Back means output. Feedback refers to taking the output and connecting it to the input terminals. In the implementation of this concept, output is not connected directly to the input. In between, there exists some manipulation. The circuit that manipulates is called feedback network or beta network. It is useful in several different ways in the design of amplifiers, like stabilizing the gain, adjusting their impedances, etc., even to convert them into oscillators. Feedback, as already mentioned, is used to improve the performance of the amplifiers. We are going to see it is also useful to convert amplifiers into oscillators. Here is shown a simple block diagram of feedback amplifier. Basic amplifier is shown. A is gain of the amplifier. This gain can represent voltage gain, current gain, resistance, even transconductance, about which we are going to discuss soon in the present session itself. So this is basic amplifier. It provides some enhancement, some strengthening of the signal that is given at its input terminals. The signal source is shown here in the beginning on the left hand side. After amplification, after strengthening of the signal, it goes and appears across the external load. To make it more sophisticated, more stable, feedback is applied. Here output is taken, sampled, it is passed through a network. This network is called beta network or feedback network. And then the output of the feedback network, it is called feedback signal. It is connected to the input side of the basic amplifier. Already signal source is there on the input side. Now signal source, feedback signal, both are on the input side of the amplifier. There are two possibilities for interaction between input signal and feedback signal. We can see that feedback signal getting added to the input signal, resulting in a larger signal. In such case, the feedback is called positive feedback. We can also adjust the things in such a way that we can also design the system in such a way that the feedback signal gets subtracted from the input signal, reducing smaller amplitude signal at the input terminals of the basic amplifier. In such case, such a feedback is called negative feedback. Mostly we use negative feedback. Positive feedback is associated with certain serious drawbacks. One such serious drawback is generation of unwanted, uncontrollable oscillations. You find very few applications for positive feedback. Unless otherwise stated, feedback means negative feedback as far as the sessions on amplifiers are concerned. Now this system amplifier with feedback, here it is described as single loop negative feedback amplifier. Single loop, one can see in the structure there exists one loop. That's why it is called single loop amplifier. More than one loop can also be used, but here only one loop is there. That's why it is single loop amplifier. It is implemented with negative feedback. Notice the sign here. Feedback signal is subtracted from the input signal, so it is negative feedback. So single loop negative feedback, and it is implemented over an amplifier. So single loop negative feedback amplifier. After having some understanding regarding feedback concept, now a few important points regarding a classification of amplifiers. Several types of amplifiers. There, several classifications are also there. For example, small signal amplifiers, large signal amplifiers. Large signal amplifiers are also called power amplifiers. Low frequency amplifiers, high frequency amplifiers. Narrow band amplifiers, broad band amplifiers, tuned amplifiers, untuned amplifiers. Like that, several classifications are also there. Here, we consider one such classification. According to this classification, amplifiers can be divided into four categories: voltage amplifiers, current amplifiers, transresistance amplifiers, transconductance amplifiers. What are voltage amplifiers? Broadly, one can say that amplifiers which amplify voltage, signal voltage, or voltage amplifiers. Similarly, current amplifiers are amplifiers which amplify signal current. Similarly, one can define transresistance and transconductance amplifiers. The exact formal definitions we are going to see right now in the present session itself. To move further, this classification is based on magnitudes of input and output impedances of amplifier relative to source and load impedances respectively. Input and output impedances of the amplifier, they play an important role in the performance of the amplifier circuit. Input impedance of the amplifier, it is an important parameter which provides impedance matching between the amplifier and the circuit from which the input signal travels into the amplifier. Similarly, output impedance is an important parameter which provides impedance matching between the amplifier and the circuit into which the output of the amplifier flows into. These two parameters, input impedance and output impedance, play an important role not only in the classification but also in the performance of these four types of amplifiers. They play a significant role in case of other circuits also. Now, a few points regarding voltage amplifier. A formal definition is given here. By definition, voltage amplifier is one which provides voltage output V0 that is proportional to source voltage. V0 is proportional to Vs. Proportionality factor is AV. The proportionality factor called voltage gain, it is called voltage gain and it is indicated by AV. It should be independent of magnitudes of source and load resistances Rs and RL respectively. In practice, AV is dependent on Rs and RL and hence the gain provided by the amplifier varies with the source and load conditions. And it is a serious drawback. Amplifier is required to amplify the signal, input signal, but the amount of amplification depends on Rs and RL in practice. Rs is source resistance, RL is load resistance. Hence, when we use here some amount of gain, when we use there some other amount of gain, naturally it leads to confusion. We may not be knowing how much amount of gain is being provided by the amplifier. It is a serious drawback. So it has to be somehow eliminated. Feedback is the remedy. Okay. Mathematically, the amplifier's operation can be described by V0 is approximately AVVI. Approximation instead of equality is due to dependence of proportionality factor on Rs and RL. It is approximately equal to AV into Vs. Here is shown an equivalent circuit of voltage amplifier. Ri represents input resistance, RL external load, Vs is source voltage, Rs is source resistance, AVVI, this is amplifier's action. R0 is the source resistance of AVVI or output resistance of the amplifier circuit. Notice V0 is maximum when R0 is smallest possible, that is 0. So for a voltage amplifier, maximum output we can have when R0 is small, preferably 0. 0 R0 is possible. In such case, at least R0 should be as small as possible. It should be very much smaller than RL. Come to input side. V0 is large when Vi is large. Vi is large when Rs is small. Preferably Rs should be 0. If it is not possible to have 0, at least it should be small, very, very small. Small compared to Ri. So Rs should be very, very small when compared to Ri to have larger output. Amplifier is there to provide larger output. For larger output, just we have seen R0 should be small, very, very small. RS should be very, very small. With this small discussion, one can understand why RS should be small, R0 should be small when it comes to voltage amplifier. Here we have used a Thevenin equivalent circuit to represent source as well as amplifier. A few points regarding current amplifier. By definition, current amplifier is one which provides a current output I0 that is proportional to source current Is. The proportionality factor AI, here you can see, it is proportionality factor between I0 and Is. It is called current gain indicated by AI. It should be independent of magnitudes of source and load resistances, Rs and RL respectively. In practice, AI is dependent on Rs and RL, and hence gain provided by the amplifier varies with source and load conditions. So this is a problem, as already mentioned, in case of voltage amplifiers, and it is tackled by applying feedback. Mathematically, the amplifier's operation can be described by I0 is approximately equal to II. See, this is the definition of ideal amplifier. This is the case of practical amplifier. I0 is approximately II approximately equal to Is. Current amplifier. Here is shown the model of current amplifier. Here output is I0, output current. This I0 is large when R0 is large. R0 is output impedance of the amplifier. When R0 is large, the output of the source AI, most of it flows through RL. So I0 becomes large. So R0 should be large for good performance from this amplifier. Preferably R0 should be infinity. Infinity is not achievable, so it should be as large as possible. In fact, it need not be so large, enormously large. We can see it is sufficient for R0 to be large when compared to RL. That is sufficient. That makes the amplifier to perform reasonably well. So R0 should be very, very large compared to RL. Relatively, R0 should be large. And also notice I0 is large when II is large, and II is large when Ri, input resistance of the amplifier, is small. When it is small, most of the Is flows through Ri. So Ri should be small, preferably 0. 0 is not achievable, so one can make it small. It is not difficult to see that Ri need not be so small in absolute terms. The requirement is, we can see Ri needs to be small relative to Rs. Relatively, Ri should be small when compared to Rs. That's why for current amplifiers, Ri should be small compared to Rs, R0 should be more compared to RL. In this model, current amplifier model, Norton's equivalent circuits are used. See, the source is indicated by Norton current source. The amplifier is indicated by current source, Norton current source. Now we consider another amplifier, Transconductance Amplifier. By definition, Transconductance Amplifier is one which provides a load current IL that is proportional to source voltage Vs. Mathematically, IL equal to GMVS. This is the relation which describes mathematical amplifiers, transconductance amplifiers, mathematical relation. The proportionality factor called transconductance and indicated by GM should be independent of magnitudes of the source and load resistances Rs and RL respectively. In practice, However, GM is dependent on RS and RL, and hence transconductance provided by amplifier varies with source and load conditions. It is a drawback. To overcome this drawback, feedback is implemented. Mathematically, the amplifier operation can be described. This is practical amplifiers operation functioning. IL is approximately GMVA, approximately GMVS. Here is a model equivalent circuit of transconductance amplifier. Input side source is indicated by Thevenin voltage source. Amplifier is indicated by Norton current equivalent source. By using the arguments that are given in case of voltage amplifier and current amplifier, we can see R0 requires to be large compared to RL, RI requires to be large when compared to RS. Here, it requires to be mentioned fact that in the case of all the four amplifiers, absolute values of RI are not, they are not that much important as relative values. They are relative values. Ri need not be small in ohms, but it requires to be small relative to Rs. Ri need not be large in ohms, but it requires to be large relative to Rs. Similarly, R0 need not be small in ohms, but it requires to be small relative to RL. R0 need not requires to be large in ohms. It requires to be large compared to RL. So it is relative values of Ri and R0 that matters. Now we move to consider another amplifier, transresistance amplifier. By definition, transresistance amplifier is one which provides voltage output V naught proportional to source current Is. V naught is RMIS. This is mathematical description of the functioning of transresistance amplifier. Proportionality factor is the transresistance indicated by Rm. Should be independent of magnitudes of source and load resistances Rs and RL respectively. In practice, Rm is dependent on Rs and RL, and hence transresistance provided by amplifier varies with source and load conditions. Mathematically, amplifier operation can be described by V naught approximately equal to Rm II approximately equal to Rm Is. Here is shown the model equivalent circuit of transresistance amplifier. A TR amplifier is represented by Norton's equivalent input circuit and Thevenin's equivalent output circuit. This is a Norton equivalent, this is Thevenin equivalent. One can see for best performance from this amplifier, Ri requires to be small relative to Rs, R0 requires to be small relative to RL load resistance. Now, a few points regarding amplifier impedances, input impedance, output impedance. Actually, it is a summing up of the points which are so far discussed. For voltage amplifier to be ideal, to have AV independent of Rs and RL, its input resistance Ri should be infinite and output resistance should be 0. In practice, infinite or 0 values of these resistance are not practicable or realizable. However, by setting Ri large compared to Rs, R0 small compared to RL, the behavior of voltage amplifier can be made approaching that of an ideal one. Similarly, for current amplifier, to have AI independent of Rs, RL, its input resistance Ri should be 0, output resistance R0 should be infinity. In practice, infinite and 0 values are not realizable. However, by setting Ri small compared to Rs, R0 large compared to RL, the behavior of the current amplifier can be made approaching that of an ideal one. In case of transconductance amplifier, similarly, by setting Ri large compared to Rs, R0 large compared to RL, the behavior of the amplifier can be made approaching that of an ideal one. In case of transresistance amplifier, by setting Ri small compared to Rs, R0 small compared to RL, its behavior can be made approaching that of an ideal one. Ideal amplifier characteristics are put in a tabular form here. Input resistance for voltage amplifier, it should be infinity. Current amplifier 0. Transconductance amplifier infinity. Transresistance amplifier, it should be 0. R0. For voltage amplifier, it should be 0. Current amplifier infinity. Transconductance amplifier infinity. Transresistance amplifier, it should be 0. Transfer characteristic is voltage amplifier V0 equal to AVVS. For current amplifier, it is IL equal to AI by AI into IS. For transconductance amplifier, it is IL equal to GMVS. For transresistance amplifier, V0 equal to RMIS. With this, we come to the end of the session. In this session, the focus is on amplifiers and on the need to implement, to apply feedback to this amplifier. Hope this session is useful to you. We meet again in another session soon.